This time we're going to discuss about one of the applications of data structure tree, which is called game tree. A game tree is a tree representation of a two-player game such as tic-tac-toe, chess, dama, which is called the Filipino checker game, and many other two-player games. In a game tree, each node represents a game state. And for board games such as dama, checkers, draughts, or chess, these game states are called board game states. And the branches of a game tree represent transitions to each possible next states after a legal move is made. So again, in a game tree, which consists of nodes and branches, the nodes in a game tree represent the game states. For board games, these are called board game states. And the branches of a game tree represents transitions from the current game state to the next game state after a player makes a legal move. And among these nodes in a game tree, some of these are called leaf nodes or simply leaves. And the leaves of a game tree or the leaf nodes of a game tree represents terminal states or terminal game states. Terminal because this is when the game is already over. Okay, so this is when the game is over and therefore it has already an outcome. So each leaf node is labeled win or lose or draw. And these three are, of course, the three possible outcomes of a two-player game. So say we take tic-tac-toe as our example. Tic-tac-toe is a two-player game where the two players make use of the two marks X, say maybe for player 1, and the mark O for player 2. In a tic-tac-toe game, each player will take turn putting his mark on any vacant square where the board is consisting of 9 squares. And initially, at the start of the game, these 9 squares are vacant. So say this is the initial board state. It has 9 squares. And say for example, at this point, player 1 with X mark is going to make the first move. So this is X turn. For X, there are 9 possible legal moves, right? X could put the mark here, so resulting to this game state. This is the root node of the tic-tac-toe game tree, and we call this one here as a branch, which is a transition from this current game state. This one is the current game state, and this branch represents the transition from this current game state to this next game state. And this transition is done when a player makes a legal move. So this branch also represents a legal move, like putting the mark of player 1, which is X, on this vacant square, resulting to this next game state. But if the player, the X player, puts his mark on this square, the next game state would be this one, right? And if the X player choose to put the mark here, then the next game state is this one. Okay? So from the current game state, which is this one, where all the 9 squares are still vacant, from this current game state, there are how many legal moves available for player 1 or for player X? There will be 9 legal moves, right? Which means there will also be 9 transitions, right? The first legal move is, say, putting the mark here. And then the next legal move is putting the mark on the next game, on the next square, resulting to this board state. And then the next legal move, which is the third legal move, would be placing the mark on this square. And so there will be 9 since there are 9 vacant squares. One legal move is to put the mark here. Another legal move is to put the mark here. Another legal move is to put the mark here. Another legal move is to put the mark here, and so on until this one, putting the mark on this square. So the game tree now would look like this one, where we call this the root node, where all the 9 squares are still vacant. And say if at this point X player is going to make the first move, then there are 9 legal moves available for him to make. So if we're going to draw the complete game tree on this level, there will be 9 transitions, right? So we have 1, 2, 3, 4, 5, 6, 7, say 8, and then 9. So this is first legal move, second legal move, third, fourth, fifth, sixth, seventh, eighth, and ninth legal move, or 9 transitions. And say this is what we call the current game state. Each of these nodes here, we call this the next game states. So the first one would be putting the mark here. The next possible game state would be this one with the mark on this square. And the third possible next state would be this board state having the mark in here. And then the fourth possible next game state would be this board having the mark here. And the fifth would be having the mark here. And then the sixth would be having the mark here. And the seventh would be having the mark here. And the eighth would be having the mark here. And the ninth, or the last, would be having the mark here. So these are all the possible next game states. There are 9 because there are 9 possible legal moves from this initial game state. And on this level, the second player, player O, would make the next move because X and O players take turn making moves. So the first to make a move at the start of the game, which is the root node of the game tree, is X. And on this level, it would be the next player who will make the next move, which is player O. Say for example, if this is the legal move that player X made at the start of the game, so this is the next game state. And at this point, how many legal moves are there available for player 2 or for second player to make? There will be 8, right? Because there are 8 vacant squares. So player O could place the mark here, or here, or here, here. So any of the vacant squares. Player O can place his mark on any of the 8 vacant squares. So there will be 8 possible legal moves to make, and therefore there will be also 8 possible next game states from this current game state. So we'll have 8 transitions: 1, 2, 3, 4, 5, 6, 7, 8. And this one also will have 8 transitions, right? Leading to 8 next game states. This one also has 8, up to 8. And this one also has up to 8. This one also has 8 transitions. This has also 8 transitions. This one also has 8 transitions. This one, 8 transition. And lastly, this one has also 8 transitions. Now, on this next level, the next to make a move is player X because they take turn making moves. So say for example, this is now the game state XO. Say on this level, player O places his mark here, so resulting to this next game state. And then on this level, X will make the next move. So how many legal moves are there available for player X to make? There will be 7, right? Because there are now 7 vacant squares. From original 9 vacant squares, here we have 8 vacant squares. On this level, we now have 7 vacant squares. So all the nodes on this level, including this one, when it is the time for player X to make the next move, each node on this level will have how many transitions to the next game states? There will be 7. Each of the node here will have 7 legal moves. Say we're going to construct a complete game tree for tic-tac-toe game, but let us just start at an interior node so that we will not be constructing a huge game tree. So say we are going to start at an interior node, which is this one, X, 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 O, O, and O. Say for example, this is the root of the game tree. Okay, this is just an example because in reality, the root of the game tree for tic-tac-toe game is the board state with all 9 squares still vacant. But since that would create a huge tree, so for the sake of illustration on how to construct a game tree, let's just start with this interior node. Say for example, at this level, the start of the root of the game tree, X will make the next move. So how many available legal moves are there for X? There will be 3 because there are 3 vacant squares. This one, and this one. So since there are 3 legal moves, there will be also 3 transitions. So say this is the first, the second, and the third. So the first next game state would be this one, X, 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 O, O, and O. So placing the mark here would result to this game state. And the second would be placing the mark here. And the third would be placing the mark here. So again, there are 3 legal moves because there are 3 vacant squares. If player X would choose to place the mark here, then it would result to this game state. Or if player X would choose to place the mark here, then it results to this second game state where the new mark is here. Or player X could choose to place the mark in here, resulting to this third game state where the mark is here. On this level, it is the turn of player O. So for any of these 3 possible game states, this one, or this, there are 2 available legal moves for player O because there are 2 vacant squares. This one, there are 2 here, there are also 2 here, there are also 2 vacant squares here. But notice for this game state, the first one here, we already have a game outcome, right? Because for tic-tac-toe, when will the game tic-tac-toe end? It ends when any player makes a straight 3 marks, either horizontal straight 3 marks or vertical or diagonal. So if any player makes a straight 3 marks, either horizontal, vertical, diagonal, then that player wins the game. And aside from that, the game would also terminate or end when all squares are already marked, meaning there are no vacant squares anymore. So that is another condition for the end of the game. So there are 2 conditions. Either one player has already made 3 straight marks, horizontally, vertically, or diagonally, or all the squares are already marked and there is no winner or loser. So this would be a draw outcome. So for this game state, player X has already made a straight 3 marks and therefore this is considered a leaf node. So this is a leaf, meaning that's the end of the game, and the result here is X wins. So in this game state, player O cannot make any more move because the game is over in this game state. So we consider the next game state. Now, this is not a leaf node yet because there's no winner or loser yet, and there are still 2 vacant squares. So player O can continue placing the mark O on any of these 2 vacant squares. So since there are 2 legal moves, there will also be 2 transitions. So say this is the first one and the second one. The current state is XXO, O, XXO. This is also XXO, O, XXO. So if player O choose to place the mark here, that would result to the next game state, which is this one. Okay? So the mark O is this one in here. And if player O choose to place the mark in here, in this square, then that would result to this game state where the mark of O is in here. For this third game state, again, there are 2 vacant squares and no player, either X or O, has made a straight 3 marks yet. So this is not yet a leaf node, or the game is not over yet for this game state. And so, since there are 2 vacant squares, there will also be 2 transitions or legal moves. So let's say this is the first one and this is the second one. For the first one, this is the current state is X, X, O, O, X, X, O, and this is also X, X, O, O, X, O, X. So if player O will place the mark here, that would result to a mark O in here. And if player O would choose to place the mark here, that would result to the next game state, this one, where the mark of O is here. So on this level now, it is the turn for X to make the next move. And if we're going to check the next game states on this level for X, is this already a leaf node? This is not yet a leaf node because no player has made a straight 3 marks yet, and there is still a vacant square. One vacant square in here. So we will still be continuing the game, and this time it is player X that will place the mark on the vacant square. So that would result to one transition only since there is only one vacant square left. So this is, the current state is X, X, O, 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 X, X, O. Placing the mark for X here on this square, vacant square, so X is in here. Now for this game state, take note that player O has already made 3 straight marks. So this is now a leaf node, and the outcome of the game in here is O wins. So since this is now a leaf node, it is a terminal state. Therefore, we cannot continue with the game anymore at this point. And then how about this one? Is this a leaf node? This is not a leaf node since there is no player who made a straight 3 marks already, and also we still have one vacant square in here. So we continue the game, and since there's only one vacant square left, there will also be only one legal move or only one transition. So the current state is X, X, O, 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 X, and X, O. The vacant square is this, so we place the mark of X in here. The next game state is this one, and this is not yet a leaf node because there is no player, either X or O, that has made a straight 3 marks. And there is still one vacant square, which is this one. And so we continue the game for player X now. And since there's only one square, it means also that there is only one legal move or transition. So the current game state is X, X, O, O, X, X, O, and O. So the vacant square is here. So we place the mark of X in here. This is where we place the mark of X. So if we're going to evaluate now all the nodes, this one is a leaf node. The game is over at this point. This one is also a leaf node. Game is over at this point. And what is the outcome of the game? Is it a win for a player, a lose for a player, or is it a draw? It is a draw. So this one is a draw. And how about this one? This is a leaf node. So in here, O wins. How about this one? This is a leaf node since all the squares are already marked. But since there is no player that makes 3 straight marks, then this is a draw. The outcome of the game is a draw. How about this node, the last node? Take note that X here made 3 straight marks. And so, this is a leaf node and the outcome of the game is X wins. After we have constructed a tree representation of any task or processes such as this two-player game tic-tac-toe, we usually need to obtain answers to some questions about the task or process that the tree represents. In the case of game trees, the questions that we usually pose at the start of the game or at any game state is, what is the probability that I will win this game now that I am in this game state? Or you may ask, at this current game state, what should be my next move so that I will win this game? And for you to be able to answer these questions, you need to know the objective evaluation value of the current game state, which means you need to know the evaluation values of all possible legal moves available to you at the current game state, so that you will know the best legal move to make to maximize the likelihood of you winning the game. And so, before deciding to make a move, the player has to do exhaustive search. Okay? Exhaustive search for the best move leading to a win game outcome. So in order for the player to make the best move among all available legal moves, the player has to do exhaustive search in the game tree. This exhaustive search for the best move is called backtracking. So we call this exhaustive search method as backtracking. So for this particular tic-tac-toe game tree, say if we are currently at this game state, okay, so say this is the current game state, and at this game state, it is player X that will make the next move. Now, if you are player X, you have 1, 2, 3 legal moves to choose. And before you can choose, you need to do exhaustive search in the game tree. So what players normally would do is, before they would decide what best legal move to make, they have to spend sufficient time to think about all the legal moves available to them. And then in their minds, they would be traversing this game tree, starting with this, to evaluate this legal move. What would be the possible outcome of this legal move? And then after that, it would visit this next legal move. What will be the outcome of this next legal move? And to answer that, you need to visit all of the possibilities. Okay? So what the player actually does, either player X or player O, what the player actually does in his mind is, he traverses the whole game tree starting from this current game state as the root. He would traverse the game tree by doing depth first search traversal, visiting all the nodes in this fashion. And the purpose of the exhaustive search or the depth first search traversal of the game tree is so that he will be able to determine which of the available legal moves is the best move to make, so that he will eventually arrive at the win game outcome. So this backtracking or doing the depth first search traversal exhaustive search of the game tree is the player's way of looking ahead. Okay, so that is the process of looking ahead by doing traversal or traversing the game tree to in search for the best path from the current game state to the nearest win outcome. So the process of backtracking, which is exhaustively searching or traversing the game tree by doing depth first search traversal starting from the current game state, you visit all the nodes of the tree, all the descendant nodes, until you reach back to the current game state, the current node. And after you have visited all the nodes of the subtree, the player will then be able to determine which of the possible available legal moves is the best move that will lead him to a win outcome. And that win outcome is, of course, the nearest win outcome, because there are many other possible paths leading to a win outcome. So the player has to choose the best path, and that is the soonest time to win the game. And as the player does the game tree traversal or backtracking exhaustive search, visiting all the nodes from the current game state or current node, visiting all the nodes, the player will evaluate each node or assign evaluation value to all the nodes or to each nodes until finally he will be able to assign an evaluation value for the current node. And that evaluation value of the current node will tell the player what is the probability of him or her winning the game.